I forgot. Okay, discussing about the elastic potential energy, I have told you that there are certain materials which can be compressed or stretched by applying the force, and these type of materials are called elastic materials. And when we release the force on these materials again gain their original shape. So these are elastic materials. When we press them, when we put force on them to compress or stretch, we are doing work on it. And whenever we are doing work on that body, it means that work is stored in some form of energy, and that type of energy is called elastic potential energy. I hope you are clear with that. Now, as in case of kinetic energy and in case of potential energy, we had different formulas to find that energy, the amount of energy which is stored in that body. Similarly, in this elastic potential, in the case of this elastic potential, we again have a formula which we need to understand. Basically, the elastic energy is generally equal to half k e square. Now we need to understand what is k, what is e. Uh, Basically, the k is you can consider an example of a spring, that if the energy is stored in that elastic material in that spring. So that this k is basically, what does this k means? This k is basically the spring constant. It is the property of that spring, which depends on which varies with different type of springs, that how much compressible or how much stretchable that spring is. This k means the spring constant, which shows the property of the material, that how much this spring is stretchable or compressible. So this is k. And what does this e means? In some cases the formula is written as e is equal to half kx square. These both are the same formulas. In one notation it is written as half ke square, and in the other is kx square. Now what does this x means? X is that displacement which we covered during the extension. Like let me explain it to you with an example. Let us say we have this spring, and this is in its relaxed position. We are not applying any sort of force on it. Now let us say that we have applied a force, and this spring is just expanded. Now the distance from this equilibrium position to its stretched position is called the extension, and this is what we mean by this e or x. You got my point? What is e or what is x? The extension in
Yeah.
this spring which is produced by applying the force.
Okay.
This is how we can find the energy in that particular spring. So let us see what is written over here in your notes. Basically, stretching or squashing an object can transfer energy to its elastic potential energy. As I have told you, the elastic potential is energy is basically stored in due to stretching or compressing of a elastic material, so long as the limit of proportionality has not been exceeded. Now this is an important point. What does this limit of proportionality means? I have told you that we just consider this example of spring. We just put some force on it, it just get extended, and when we remove the force, it just came back to its original position again here. So now imagine what happens if we apply so much force that this spring becomes permanently deformed. Like, let us say we have applied so much force that this spring gets this shape, and now when we release that force, now the spring doesn't get back to its original shape. So it means that you have exceeded its limit of proportionality, or its elastic limit has been exceeded. So this is what I mean, what it meant by as so long as the limit of proportionality has not been exceeded. That if this limit is exceeded, this equation will not hold true. Is it clear to you?
Yeah, yeah, I get it now.
Oh, okay. Energy store of stretched spring can be found using this formula. We have already discussed this formula. So now moving forward,
Okay.
what else we can study in this? Let us see. Make the most of your potential. Okay, there is a question given here. We can do that in the second half of this class when we will be solving the problems. I have downloaded some other worksheets for you as well. So we will
Okay.
do it at that moment of time. Now, moving towards specific heat capacity. What does this mean? Basically, we need different types of energies in order to heat a material. This specific heat capacity is basically related to the thermal energy store of a body. So what does this means by a specific heat capacity? You can define the specific heat capacity as that the amount of heat you require or you need to raise the temperature of a body. Are you getting my point? The certain amount of heat you need to raise the temperature of a body. Now it can be different for different materials. Some materials need little energy in order to raise its temperature, and some materials need more energy in order to just raise or increase its temperature. Are you getting my point? So this property of materials is called specific heat capacity. Are you getting my point?
Yeah.
Okay, so let us see what is written over here. It says that the specific heat capacity is just a scientific terminology, which is another way of saying that how hard it is to heat something up. That how much energy is required or how hard it is to heat a material. So different materials have different heat capacities, as I have told you earlier. That different materials need different energies in order to raise their temperature, and there will be a definition of heat capacity somewhere over here. Okay, just look at the point number 3. Specific heat capacity is the amount of energy needed to raise the temperature of 1 kg of a substance by 1 degree centigrade. This is the proper definition of specific heat, that you have a certain amount of material. What is it? That you have 1 kg of certain material and you want to raise its temperature by 1 degree centigrade, then the energy you need for this purpose is called the specific heat capacity. I hope it is clear to you.
Yeah.
Okay, so moving towards the first point, more energy needs to be transferred to the thermal energies of some materials to increase their temperature than at the others. As I have told you, that we need different amount of energy for different materials in order to raise their temperature by 1 degree centigrade. For example, you need 4200 joules to warm 1 kg of water by 1 degree centigrade, but we need 139 joule. You can see the energy difference, that for the water there is a huge amount of energy required to increase the temperature by 1 degree centigrade, but in case of mercury, you can see that only 139 joule is enough to raise its temperature by 1 degree centigrade. So both of these materials, water and mercury, have different heat capacities. So moving towards the second point, it's written that materials that need to gain lots of energy in their thermal energy stores to warm up also transfers loads of energy when they cool down again. Okay, this is again an important point, that those materials which need more energy in order to be heated, they will release more energy when they are being cooled down. That when they are losing heat, they will again lose much of the energy if they need much energy in order to get heat up. So I hope this point is also clear to you.
Wait, sorry, can you repeat that again?
Okay, for sure. Basically, if let us say a material needs, let us take the example of water and mercury over here. That we have said that water need 4200 joule to warm 1 kg of water. We need 200 4200 joule energy to warm 1 kg of water by 1 degree centigrade. So it means it takes a lot of energy in order to be heated. On the other hand, mercury needs a little energy in order to just get warm by 1 degree centigrade. So you can say it in some other ways. You can say that water stores more energy in it while mercury stores little energy in it. So we can say that if a material needs more energy to get heated, it will also release more energy when it cools down. That when you are cooling that material down, it will release more energy as compared to mercury. That when you cool down the water, it will release more energy as compared to mercury. Do you get my point?
Okay. Yeah.
So it means that we can say that water can store more energy as compared to mercury. So now moving towards the concept of specific heat capacity. The word capacity, from the word capacity you can guess that it is some sort of store. So specific heat capacity, a material having larger store of energy will have larger amount of specific heat capacity. Are you getting my point?
Yeah.
Here we again have a certain equation in order to find the specific heat capacity, and it is written over here. You can see that specific heat capacity, what does it is equal to the change in thermal energy of a body is equal to mass of that body. M is the mass, C is basically the heat capacity we are talking about, and delta theta is the rise in that temperature, the temperature we are changing. So from this you can see that the C, or the specific heat capacity, is equal to change in energy divided by M delta theta. So we can define the specific heat energy from this expression as well. How? Basically, the amount of energy delta E, the amount of energy you require to heat 1 kg of a body, 1 kg of a body, in order to increase its temperature by 1 degree centigrade. So this is how we can define specific heat capacity. I hope you are clear with the concept of specific heat capacity.
Yeah, I'm just copying the last part down in my book.
Okay, you can write it. You can take the time, and you can ask me to just give you some time in order to write it down.
Okay, yeah.
Okay, let me know when you are done with writing.
Done. Yeah.
Okay. Okay. So moving forward, do you have any question related to specific heat capacity? You can ask.
So let me see.
It's sort of a new topic, like you might have not studied it in your earlier classes, so that's why I'm asking you to take some time, and if you have any doubt or questions you can ask, so that when we are clear with it we just move forward.
I don't have any at the moment. No.
Okay. Okay, read it after the class, and if you have some questions we can discuss it in tomorrow's class.
Yeah, okay, no.
Okay. Okay. So there is some practical work. Do you want me to study it? Should we discuss this practical? It's a practical demonstration that how we can calculate that the specific heat capacity.
Okay, yeah, let's do it then. Yeah.
Okay. There is a practical in which it's given that how we can find the heat capacity of a material. So in the first step, to investigate a solid material like, for example, copper, you will need a block of the material with two holes in it for the heater and thermometer. Basically, you can see in this figure that if we want to investigate a solid material, we need to have two holes in it, like this hole and the second one this hole. Why we need these two holes? In the first hole we just used to supply the heat in that particular substance, if of which we need to find the heat capacity. And in the second hole, we just put the thermometer in order to keep an eye on the temperature, on the change in temperature. So in the second step, the mass measure the mass of the block, then wrap it in an insulating layer, example a thick layer of newspaper, to reduce the energy transfer from block to the surroundings. Now what does this mean? It is saying, first keep in mind that what are the requirements in measuring the heat capacity. We need, as I wrote the formula, we need to find the change in energy, we need to find the mass of the body, and we need to find the change in temperature. So first of all, you need to measure that mass, which you need to find the heat capacity, and then you wrap it in some insulating material. Why we are doing so? If it is not insulated, whenever we heat a body, it will it will release its energy, or it will release its heat to the surroundings. As long as it cools down with the surrounding, or as long as it becomes it comes in equilibrium, in thermal equilibrium with that surrounding. So we need to, that's why we need to insulate that body. And how we do so? We just cover it or wrap it with some insulating layer like newspaper or some plastic layers. Insert the thermometer and heater as shown on the right, and then in the next step, you just put the thermometer and the heater. From the heater, we can say that it is a source of heat we are providing. Then measure the initial temperature of the block and set the potential difference V of the power supply to be 10 volt. Then in the next step, what you are doing is you are measuring the initial temperature. Why we are doing this? Because we need to find delta theta. And what does this delta theta means? Delta theta means theta 2 minus theta 1. Delta means change. You know that, I hope. Hello.
Yeah.
Okay. Delta means change. What does this delta means? Delta means change. Now theta is temperature. Here we are representing temperature with
Is
theta.
delta the triangle?
Uh, no, basically in this case, it's just it is just a representation of temperature. You can write delta T as well. Delta T.
Yeah.
Delta means change. That this little triangle is delta, and it means change. And T means temperature, or theta means temperature. So we are measuring the change in temperature because it is important. Why? Because we have seen that the heat capacity is equal to delta E. It means change in energy, and divided by m, the mass of the body, and delta theta or delta T. Delta theta and delta T are same thing, the change in temperature. So we need to find all these parameters. First we made the mass, now we are finding the delta theta. So how we will find? We will find the temperature before we provided the energy, and then we will find the theta after we provided the energy, that how much theta is changing, its initial value when the energy was not supplied to that body, and its final value when the energy was supplied to the body, that how much temperature is changed by that amount of energy. Are you getting my point?
Yeah.
So this is how delta theta will be theta 2 minus theta 1. It means that final temperature minus initial temperature. And so in this step, you will find the initial temperature, which you need to find before this supply of heat. And then after that, you just initial temperature of the block, and then you set the potential difference of V of the power supply. You are providing that energy through this power supply, you are heating it through this power supply, and set the potential, a fixed potential, which is 10 volt, and then turn on the power supply and start a stopwatch. And then you just provide that, turn on the power supply for a certain amount of time, and you just measure that time. When you turn on the power, the current in the circuit, that is moving charges, does work on the heater transferring energy electrically from power supply to the heater thermal store. uh, it's just saying like you know how things which example should I give? You know the iron which we use to press our clothes.
Oh yeah.
So how it works? Basically, it takes energy, electrical energy from our like home or from our sources, from the circuit. It takes the electrical energy, and that electrical energy is provided to the heater of that iron, and it gets heated, and then we use that heat. You are getting my point?
Oh, so from electrical energy to like thermal.
Yes, we convert that electrical energy to thermal energy, and then you utilize that thermal energy. So same is the case here. We use the power supply, this electric power supply, and we convert that this electric power by using a heater. We transfer its electrical energy to the thermal energy, and then thermal energy is provided to this mass of copper. So we are providing the heat to that body. We are providing the energy to that copper bar, or you can say mass of the copper. The energy is then transferred to the material in the form of thermal energy, and by heating, causing the material's temperature to increase. Now when we are giving it heat, its temperature will rise. So what will happen next? In the next step, as the block heats up, take the reading of the temperature and the current I every minute for 10 minutes. You should find the current through the circuit doesn't change as the block heats up. Now you see that what will you do? You will take the readings for the next 10 minutes, reading of temperature. You will see the temperature will rise gradually. When you have collected enough readings, 10 should do it. Turn off the power supply. Using the measurement of the current and the potential difference of the power supply, you can calculate the power supplied by the heater. Now we know that the formula is of the power is P is equal to VI. We set up the values of voltage, right? We have it was 10 volt. We already fixed it. We measure the values of current for during this experiment for the 10 minutes. So we find the value of current. From this, we just multiply these two values to find the power, and we know what power is basically energy per unit time. That the energy that how much work a body can do in a certain time. So uh, we have find out the power, and we measure the time by using the stopwatch. So this is how we can get the energy by multiplying that power which we calculated from the product of V and I, and multiplied it with the time it took for the experiment, and then we will get the energy. Now you can see that we are equipped with all the necessary parameters which are needed to find the C. We have C is equal to, what does we have? We have C is equal to delta E divided by M delta theta. So we find out the mass in the first step. In the next step, we find out the change in temperature, that after 10 minutes, what is the temperature minus after 10 minutes of power supply, turning off power supply, we find out the temperature, and then we subtract the initial temperature which we noted down before turning on the power supply from this, and this is how we find out the delta theta. We have find out the mass, and from this product of power and time, we find out the change in energy. So we just divide these things, this change in energy with mass and the change in temperature in order to find the C. This is how we can find out the heat capacity of a material by just calculating all these parameters, and by doing this experiment. I hope this experiment is clear to you.
Yes, it's clear.
Okay. Okay. So in the next steps, you can read it out. It will be the same thing. I don't think so. There will be any thing which you might not know. Let us read it. By the way, we can see that is there anything which we have not discussed yet. Now, from the point 6, when we have collected the enough readings, then we multiplied the voltage and current in order to find the power, voltage and current in order to find the power, and then you can use this to calculate how much energy has been transferred to the heater at the time of each temperature reading. Using this formula, we have discussed it, we have also discussed this, and because we calculated the time as well, so we calculated the energy. Now if you assume all the energy supplied to the heater has been transferred to the block, you can plot a graph of energy transferred to the thermal store of the block against temperature. It should looks like something like this. The graph between the change in temperature and the energy transfer should be like this. Why this is like this? You may or may not get the curved bit of the being. Don't worry about it. It is saying that you might get a straight line like this as well, that we are providing the energy and it is raising the temperature of the body linearly. So find the gradient of the straight part of the graph. This is delta theta divided by delta E. Now we know, do you have the concept of slope?
Oh, slope?
Slope, yes.
No, we haven't. Like when there's a like rise in it, like when it's steep.
Basically,
The
slope
graph.
is the steepness of a graph. There is a formula of slope. Slope is basically y2 minus y1 over x2 minus x1. You can find the slope of a graph by just, let us say, taking 2 points on it. Just give me a second. Okay, by considering 2 points, any 2 points on the graph, let us say this point and this point. Consider this is point 2 and this is point 1. Now there will be a value on the x-axis of this point, and it will be considered as x2, and a value on the y-axis on with this corresponding to this point, and it will be considered as y2. And similarly, for this point, consider a point corresponding to this on y-axis, and it will be y1, and on x-axis it will be x1. Now just if we use this formula, y2 minus y1 over x2 minus x1, we will get the slope of this of this graph. Now in this particular graph, we can have anything on x and y axis of a graph, and the slope, and then we can find the slope of any of those parameters. But in this particular graph, on the y axis we have temperature, and on the x axis we have energy. So the slope is, what does the slope will give? It will give delta theta. It means that the change in temperature divided by delta E with respect to the change in energy. You know from the equation above that delta E is equal to delta MC delta theta. So the specific heat capacity of the material of the block is the 1 by the gradient of the gradient into mass. It is saying the same thing, that in the case of C, we have delta E divided by delta theta into m. We had this formula. So if you see that delta E or delta theta is equal to 1 by the slope or 1 by gradient of this curve into mass. So this is what it is trying to say, that the heat capacity will be equal to the 1 by gradient into the mass of the block. You got my point?
Yeah.
If
So
you have
do you know,
any doubt, you can ask.
do you know in exams, would you be expected to like find the slope in some tests?
Yes, it might be given a figure to you of a similar figure like this one for the change in temperature with respect to energy, and the mass of that material is given to you, and you might be asked to find the heat capacity of that material. So how you will do that? You will just find the slope first, or slope or gradient. Slope and gradient are same things. Okay, so you can find the slope or gradient of that curve, and then you multiply the mass with it, and then you just take the reciprocal of that value, and it will give you the specific heat of that material.
Okay.
So is it clear to you the concept of
Yeah,
specific heat?
yeah, it's clear now.
Okay, so let us move forward. There is again a question given. We can solve it in the next half of the class. Moving forward to conservation of to the concept of conservation of energy and power. I guess we had discussed a bit of conservation of energy in the first class, and now we will be more
Oh
focused on
yeah.
power. So let us just revise that concept of conservation of energy. That what is the conservation of energy? Uh, let us start with you. Can you please explain what does this mean? We have discussed it in the first class. That what does conservation of energy means?
It's that the energy can be created or destroyed, but only transferred.
Yes. Transfer to what?
Transferred from one energy store to another.
Exactly. This is what the conservation of energy means. As you can see that the word conservation means that something is not changing. It something is constant. So in what does this conservation of energy means? It's mean that the total energy of the system will remain constant, although it can be just transferred from one energy store to another. It can be converted from gravitational energy to gravitational potential energy to kinetic energy, or it might be converted from kinetic potential energy to gravitational energy, or it might be converted into any other form of energy, but the total energy of the system will not change. It will always remain same. So energy is never destroyed, or energy can never be created, is the conservation of energy. It is what the conservation of energy means. Acha. Make sure you learn the fact that it's really important. You need to know the conservation of energy principle. Let us read it out. What does these notes says? These notes says that the conservation of energy principle is that the energy is always conserved. Energy can be transferred usually usefully from one body or another, or it can be lost, or it can be transferred to an energy store which might be less useful to us. And when it is transferred to that energy store, or that type of energy which is not useful for us, it will be we call it as energy dissipation or energy loss, that this energy is lost. But actually this energy is not destroyed. Let me give you an example. That for example for example which example should I give to you? Let us say we turn on an electric bulb. What we are doing with it, we are giving the electrical energy to that electric bulb, and it's giving out the energy in the form of light. So this light is useful to us. This light
Yeah.
is a useful energy store for us. So this energy is used or transferred or stored. But when we touch that lamp, or when we touch that electric bulb, it you can feel that it gets heated after being turned on for an hour or 2 hours. You can feel that it is hot. So some of that in the electrical energy is lost in the form of heat as well. So it is some of it, we can say that some of its energy is transferred to the thermal energy store of the bulb, but that thermal energy store of the bulb is not useful for us. So we can say that that particular amount of energy is lost. Are you getting my point?
Yeah.
If you
So
have
wait, you're saying is with a light bulb, when we use the light from the light bulb, but it gives off heat, and
uh,
that heat is
I'm saying that if your light bulb is turned on for, let us say, 1 hour, or let us say for 2 hours, then after the
yeah,
2 hours, when you touch that bulb, you will feel that it gets heated.
Yeah.
You can try it at your home as well, that it will be heated. So it means that most of the energy, the thermal the electrical energy, is transferred to the light energy, which is useful for us. And we call it, or we say that most of the electrical energy is transferred in light energy store of that body, of that bulb. But some of its energy is also dissipated, or some of its energy is also lost in the form of heat. Some of some of the electrical energy is transferred to the thermal energy store of the body, but that thermal energy store of the body is not useful for us. So we just say that this amount of energy is lost, or this amount of energy is dissipated, or this amount of you can say that this amount of energy is not useful to us. So is it clear to you?
Yeah.
Okay. When energy is transferred between the stores, not all of the energy is transferred usefully into the stores that you want it to go. Some energy is always dissipated when the energy transfer takes place. So this is what I wanted to explain it to you. Basically, you can read this second point, that when the energy is transferred from one store to another, all the energy is not transferred from that particular store to the to that store which you want to be it to be converted. Some of the energy is dissipated, or some of the energy is transferred to those stores which are not useful for us, or which are not which we don't need, or we don't want the energy to be transferred. So you got my point.
Yeah.
So that amount of energy which is transferred to those energy stores which are not useful for us are called is called dissipated energy. So this dissipated energy is sometimes also called wasted energy, because this energy is not useful for us. The heat by the bulb is not useful for us, although light is useful for us. And this that but the heat energy that is produced by the bulb is not useful for us. So we say that this energy is wasted. This is wasted energy, because the energy is being stored in a way that is not useful, that we don't wish it to be. So let us say an example is given over here. A mobile phone is a system. When you use the phone, energy is usefully transferred from the chemical energy store of the battery in the phone, but some of this energy is dissipated in the transfer to the thermal energy store of the phone. Similarly, as I gave you the example of a bulb, you can understand it from the example of a mobile phone or a laptop. You turn a laptop on for quite a while, and then when after some time the laptop gets heated, so most of the energy is converted to the useful energy store of the laptop, but some of the energy is converted to the heat energy of the laptop, and heat energy of the laptop is not useful for us. Are you getting my point? So this energy which is converted to the heat energy of the laptop is called wasted energy or dissipated energy.
Okay.
Are you following me till here?
Yeah.
Okay. So the next thing, there is another example given over here, I guess. You also need to be able to describe energy transfer from the closed system. We have discussed the system. What is the system means? Anything we are observing, or anything in which the energy is being transferred is called a system. So an example is given. Let us say a cold spoon is dropped into an insulated flask of hot soup, when which is then sealed. You can assume that the flask is perfectly a perfect thermal insulator. So the spoon and the soup from a closed system forms a closed system. A closed system is the one in which that energy can neither be taken out, or we cannot provide the energy to that system. Are you getting my point? So this is what a closed system means. We have discussed it in the last class as well, that a closed system is one to which we don't provide heat, and from which we don't take the heat out. It is a closed system, that the energy of that system is not changing. So in a closed system, let us say we have a bowl of hot soup, and in that hot soup you put a cold spoon, and then you just take that hot soup and the combination of hot soup and the cold spoon, and put it in an insulated flask. An insulator is a body which which don't allow the transfer of electric current or energy from it. You cannot pass the electric current, or you cannot pass the heat from it. So when you put that combination of hot soup and closed spoon in that thermal insulator, it means that you have a closed system which is the combination of spoon and soup. So energy is transferred from the thermal energy store of the soup to the useless thermal energy store of the spoon, causing the soup to cool down slightly. Now, what will happen? You can see that whenever a hot body and a cold body are in thermal contact, the hot body will give its heat to the cold body, and the cold body will gain the heat from that hot body. The hot body will get slightly colder, and the cold body will get slightly it will get a little temperature from the hot body. So you are getting my point till here?
Do you know when you said closed system,
Yes.
what does closed system mean?
I have told you that a closed system means a system or a combination of systems in which you cannot take the heat, from which you cannot take the heat out, and you can neither heat it up, or you can say that we can neither give energy to it, or we can neither get the energy out of that system. So that system is called a closed system.
Okay.
Okay, let me elaborate it to you a bit more. I guess you are confused with it. Let us say that we have a bowl of hot soup, and we just put a spoon in this. Okay, so now we just take this combination of soup and this spoon, and put it in a flask, in a box, and this box is made up of a thermal insulating material. Do you know what is an insulating material?
It's when it traps the heat. So
Yes,
like metal
yes.
is one.
It is the one which don't either let the heat to get in, or neither it let the heat to get out. So this is a thermal insulating material. Is it clear?
Yeah, it's clear.
So now when we put it in the thermally insulating material, now what happens is that this system, which is made up of spoon and soup, it can neither lose its energy, and neither it can gain the energy from the surroundings. So this such system is called a closed system, which can neither gain the energy, which can neither gain the heat, and which can neither lose the heat. So such a system is called a closed system.
And what would a normal system be like on its own, the system?
A standard system will be the one in which allows the heat transfer, or which allows the energy transfer. Let us say that when this bowl is not placed in, when this bowl is, let us say, it is not placed in the insulating box. So what will happen? The heat of this box will, some of the heat of this box of this bowl will be transferred to the surroundings as well. You see, whenever you have a hot body, and let us say you have a hot cup of tea, and you placed it in at a table. So after half an hour or after 15 minutes, the tea gets colder. Why this happens? Basically, the energy of the tea is just the energy from the tea is just taken out by the surroundings, or you can say that energy is transferred to the surroundings. So in the normal system, the energy can be transferred from the surroundings to the system or from the system to the surrounding. You can also take an example of a kettle that let us say that you just put a bowl at fire, and you just burn the fire beneath it, and after some time the water will get boiled. Why this is so? The energy is transferred from the surroundings to that particular bowl. So in a normal system, energy can be transferred to the surroundings, or by the system, or from the system to the surrounding. This is a normal system. But in a closed system, energy can neither be transferred to the surroundings, and it can neither be gained by the surroundings. Is it clear to you?
Yeah, that's better now.
Okay. So moving forward towards the concept of power, we need to understand what does the power means. Whenever in our normal use, or you can say in our normal daily life, what we means by a power is that someone, let us say, let me think an example for you. Okay, power means that how much time, taking an example of person, that how much time a person will take to do a particular job. If a person takes less amount of time and do more work, it means he will have more power. And if a person takes more time and do less amount of work, so it means that that person has less power. So power means the rate of doing work, that how fast a body or a person is doing a particular work. If a particular person or body is doing work at a higher rate, what does this mean? That it is doing the work in very less amount of time. So it means it will or he will have more amount of power. So from the formula you can see as well that what does the power means. Power means the ratio of work by time, that how much work is done in a particular time. So this is what it is meant by power. Have you got the concept of power?
Yeah.
Basically, power is the rate of energy transfer or the rate of doing work. That how much energy is transferred during the time, it is also called the power, or how much work is done in a particular amount of time, it is also again called power. Now, as for all the physical quantities we have discussed earlier, any physical quantity which we need to discuss has some units. So similarly, power has some units as well. You can see from the formula, the work has the unit of joule and the time have the unit of second. So you can say that the power will have the unit of joule per second. And what we have a common name for this joule per second, and that common name is called watt. Okay, so the SI unit of power will be watt. So I hope you are following me till here.
Yeah.
Uh,
So work done.
sorry,
What what
I
is work done?
uh,
Like it
o-
says
okay,
power equals work done over time.
yes.
What's that?
Basically, what does work done means? Okay, for example, you want to do some work. What will you need? You need. Let me explain it to you by an example. Let us say we have placed a book. I have already gave this example to you. Let us say that we have a book placed on a table. We just lift that book. What we did is we have just put some force on that, right? A pulling force on that book. And then when we just put that force, the body covers some displacement, it covered some height. Are you getting my point? Let us say okay, let me draw something for you. uh, let us say we have a box here. It is very heavy. You want to push that block let us say it is placed over here at table. You want to push that block, and what will you do? What will you do? You will exert some force on it, over it, right? Oh,
Yeah.
why this is happening? You need to put some force over here, right, in that direction. And when you will exert the force, you will push this block. It will cover some displacement in this direction. It will, let us say, after some time it will be here. It covered some distance, right?
Yeah.
So what is work? Work is basically the product of the force you applied on that particular block and the displacement this block have covered. So if you exert the force on a body and it covers certain displacement, then it means that you are doing work on that body. Do you get that point? Is is the concept of work is clear to you?
Yeah, it's more clear now.
Okay, so this is what work done means. Now if you do the work in smaller amount of time, you will have more power. Or or you can say that if a body have more power, it will require little time in order to do a particular amount of work, right? And if a body is having a less power, then it will need more time to do the same work, right? So from the formula, it
Uh,
is again, you can see it's clear that if a body have greater amount of power and work is constant, let us say work is, let us say 2 joules, then and power is and it have more power, then it needs to have to do that work in small amount of time. And if it have the less amount of power, then it will take more amount of time in order to do that particular work. Is it clear?
yeah.
Okay. So moving forward, I hope these two formulas are clear to you as well, and the units are clear to you.
Yeah, it's clear now.
Okay, so point four, moving towards the point four, a powerful machine is not necessarily one which can exert a strong force, although it usually ends up that way. A powerful machine is the one which transfers a lot of energy in a short space of time. What does this mean? It means that when we say that a person is powerful or a body is powerful, it doesn't mean that it will exert more force on something. It means that it can do more work in small amount of time, although it ends up that way. What does this mean? That usually it happens that person uh, if a person do more amount of work in a little time span or little time, then it usually have more power, right? That if or you can say it will have it will exert more force on that body. Are you getting my point?
Yeah.
Okay, so there is an example of the cars. Take two cars that are identical in every way apart from the power of their engines. Let us consider that we have two powers, sorry, two cars which are identical, which are same in every other aspect except that their engine have different powers. Both cars race same distance along a straight race track to finish the line. Both cars are in a race and they have the same distance to cover. The car with more powerful engine will reach the finish line faster than the other car. The car which will be having more powerful engine will reach fast or will win. Why? Because it have more power, so it can do the work more quickly. It can cover the distance in little time. So this is how power, work and time are related to each other, right?
Yeah.
If you have any problem related to this, you can ask.
I know it's fine. I
Okay,
don't need that.
okay, so I guess let us see this example, and then we will wind up this session, and we will start over again with the question answers. There is an example. It takes 800 joule of work to lift a stunt performer to the top of a building. Motor A can lift the stunt performer to the correct height in 50 seconds. Motor B would take 300 seconds to lift the performer to the same height. Which motor is more powerful? It is. Can you solve this problem without watching this?
Which one?
That we let us say a person, there is a person and he is a stunt performer, and it takes 8,000 joule work to lift that person to the top of a building. We have two motors for that. We have motor A and motor B. Motor A lift that person to the top in 50 seconds, and motor B takes 300 seconds to lift that performer to the same height or to the top. So the question is asking that which car will be or which lift will be, which motor will be more powerful. Can you solve this problem?
Oh, yeah.
So yes.
So motor A would lift has more power
Yes,
because the equation is because we're using 50 seconds
because
and 800 joules. So we do 800 divided by 50.
exactly, very right. And in case of
8,000
motor
divided
B,
by
we
50.
divide it by 300, so it will have less amount of power. Simple as that.
Yeah.
Right?
Yeah.
So I hope you are clear with all these concepts still here.
Yeah, I'm clear with it now.
Okay. Okay, Tala, let us take a break of 10 minutes exactly. I will just go to drink some water. You can also take a break of 10 minutes, and then we will come back to solve those questions, right?
Okay, what time should I come back?
At 9:15, sorry, it will be, what time over there is 4 p.m.
4:04.
Okay, at 4:15 sharp, right?
4:15. Okay.
Okay, in 10 minutes.
Okay.
Okay, see
All
you.
right, I'll be back.
Okay.